So MRI, if you are ever a radiographer or doctor, you will have to explain to your patient what is going to happen to them. So you also need to know what will happen to a patient when they're going to get an MRI scan. So let's see, what is the steps when you want to scan a patient?
Sign consent form.
Oh, yes. You must also know whether you have any operation or any metals in your body or not, because if there's a metal in your body and you go inside a magnet, what happened to the metal? It will just come out of your body.
Wow, the sound effect means I scared.
So please make sure no watches, no metal, no ear. What is this called? The ear.
Earrings?
You poke your ear. Earring that is metal one. Cannot.
Yeah. Sometimes they will X-ray scan the patient. So if let's say you really need an MRI and you have a screw in your elbow because you broke it before, they can put a glove or a cast around it to protect it against the magnetic field.
There are ways to do it.
If you have screws in your body, certain parts can. Screw in your brain, then cannot.
Cannot, that one cannot. Okay, Miss, I got one question. Why they call it MRI? Magnetic resonance imaging.
They call it MRI because you use magnets to align the hydrogen nuclei, and then you send some radio frequency wave to cause the hydrogen nuclei to resonate. And we use that resonance to take picture or image.
Okay. So, what about the patient again, Miss Lee?
The hydrogen nuclei in the patient, or the water molecule in the patient, gets affected by the magnetic field. Okay, so we use the magnetic field and a combination of magnetic field plus radio frequency wave to cause resonance. And based on properties of that resonance, we take a picture inside the human body, hence imaging. So using magnet to resonate hydrogen, causing us to be able to take a picture of the inside of a human body without cutting it open. That's the whole point of medical imaging. I want to see what is blocking inside without actually opening you up unnecessarily.
Good point.
Yep. So I think to start off, we will put the patient in between two poles of a very strong magnet. So it's like that picture, the donut shape. So the donut is a magnet. It's an electromagnet, of course. We will send large current through the coils. Okay. And then it's quite noisy one.
King Kong.
This magnetic field causes the hydrogen nuclei to, what's the P word again?
Precess.
Okay, with frequency in the radio frequency range. So there's a term for this called the Larmor frequency. That particular range, that signature is Larmor frequency. I'm sorry if I'm pronouncing your name wrong, dude.
It's okay.
Okay, in order to view a part of the body, so we have two magnetic fields. The first one is a very strong magnetic field. Point number one. Point number three, we need to have a secondary magnetic field. In CIE syllabus, they call it a non-uniform magnetic field. Other ways to talk about this magnetic field, sometimes it is called the gradient field. Sometimes they call it the secondary field. In case you intend to study more of this, at least these are different ways to talk about the second field. It's not the main, big, large one. It's the non-uniform. So there are two magnetic fields, strong and uniform, and then weaker and non-uniform. So the reason why we want to put a non-uniform magnetic field is because we want there to be some form of different gradient, different value of magnetic field at different parts of your body. Because I'm not going to scan you from head to toe. That would just take up too much resources, and MRI scanning are expensive and rare for hospitals to do it. So maybe I just want to scan the brain because we suspect that there's a brain tumor. So I will place non-uniform magnetic field on the body part that I want to scan. So the large magnetic field is the whole human body, but that part that I want to scan, I apply a second field. Okay, so it creates a difference so that I can take a photo. It's a bit like I put you inside a room, but I only want to take a headshot. So I shine the light to your face. The rest of your body is still lit by the ambient light, but your face is what I want. So light on the face, secondary light source, secondary magnetic field. So we're using magnetic field to take photo. Okay, so I think the patient is ready.
Okay.
Now
Get ready the buttons.
So now we shoot in, we need the hydrogen to be excited, right? So we're going to shoot in a radio frequency pulse, applying it at the same frequency. So apply at the Larmor frequency, causing resonance of hydrogen nuclei. So first we ready the hydrogen nuclei, put big magnetic field, put small magnetic field, non-uniform magnetic field. Then we send a radio frequency pulse ready to resonate. Once the hydrogen nuclei resonate, then they relax back to lower energy state. So on relaxation, the nuclei emits a radio frequency pulse. Okay? So these are the main ideas. Two magnetic field, send in radio frequency causing resonance. Hydrogen nuclei cannot stay high energy forever, will flip back down, releasing back the radio frequency pulse. Okay, so as mentioned in the previous video, our Larmor frequency depends on the strength of the magnetic field and also the different body parts, the different tissue. Fat bone water okay? And when you change the non-uniform magnetic field, different position of the nuclei can be located. Okay? So we will know, okay, this is a fat particle, but where is it exactly inside the brain? So for example, if I don't expect to see water inside the brain and suddenly I see a pocket of water, exactly where is the coordinate so that I can go into it and remove the tumor? Look, if you have a brain tumor and your surgeon can cut a 2-inch hole to remove the brain tumor, that is what you want. You want the surgeon to know exactly where the tumor is, not roughly on the left side. I don't know, I open your whole brain, there I find.
Cannot. No, that's not how we work.
Yes. So that's why we want to be able to detect the exact position. Okay. And then there's one last point that I didn't include in the typing.
Yep. Let's write it down.
So, yep. The second role of the non-uniform magnetic field means that I can choose to scan different parts of the body. So it's mainly for positioning. Later, we will show you some other diagrams to help you understand this concept better. But the non-uniform magnetic field allows the location of detection to be changed, and we can also slice the body differently. So this slicing actually allows surgeon to know for sure where the injury site, let's say you have a blocked blood vessel, like he wants to go in and remove the clot, where exactly it is. Okay, so the precision matters for organs like the brain. So the non-uniform field got two roles. One is to different position of the nuclei can be located, and I can change where I apply the non-uniform magnetic field. Maybe I apply from forward because I want to slice a certain way. I can also apply the non-uniform magnetic field from the side. So imagine taking a photo in a studio. You want to take some artsy portraits. You can shine the light from the front, you can shine the light from the side, creating some weird artsy shadow. So it's the same idea. Oh, yes. Yeah, so we're changing the non-uniform magnetic field to image the human body appropriately.
Nice. So if you open up the MRI machine you will see there's actually different parts. There is the main magnet, kind of like the main big boss B. That one will align everyone.
They never turn off unless for maintenance, so it's on all the time. Big boss is there.
Yep. Then you have a coil that will generate the radio frequency to get all the particles resonating. That's a radio frequency coil inside there. Then you have the gradient coil, which is also known as your non-uniform B.
Magnetic field.
I'm just gonna write B.
Radio frequency coil is the one that sent us the pulse, right? Send in the pulses.
Yep.
Okay.
And scanner, of course, the whole thing. Then the patient is on the table, go in. Okay, you zoom in a little bit more. In this diagram, you will see like very specific how the thing's set up. Do you need to know how this thing works? Not exactly, but it's just for you to see lah. Like, hey, look, there's many coils. So here they'll tell you all the things.
This X, Y, Z is just scanning at different orientation. Right, you have the horizontal, vertical, and the Z-axis as well. So you can see this as different coils that I can adjust in the computer, turning on the non-uniform magnetic field and controlling the image that I see, in a nutshell. Which means I can slice things differently. What is slice, Miss Ellie?
What is slice? Slice is you take an orange, you take a knife and you go
I must slice vertically, meh? I cannot bougie and slice as an angle.
You can slice any angle you want as long as you cut into slices. So actually, I have some picture of slices of brains. I mean, not actual slicing of brains, but MRI slices of brains.
I was a bit concerned there.
Let's go and see some of these slices.
Go through the slice. Just introduce the slices.
Okay, so I have here this thing that can show us the slices, and we'll look at that. It's a free software actually, and you can download the data open source because this cancer imaging archive that allows anyone to look at all kinds of scans. So what are slices? Okay, let's scroll back up to the top. So slices is this particular one is you're slicing horizontally. So currently what you see now is on top of the brain, like where my hand is pointing. And you can see the position here on the top, very small corner. And I can slowly move down. So you see the position is getting lower and lower. So I'm slowly scanning lower part of the brain. So you see the thing get bigger and bigger lah.
Slicing. Wait, not yet. Slice.
Lower. And you come to some point and you're like, wait a second, what's this, miss? We recognize this thing. Eyeballs. So you have scanned from the top all the way down to your eyeballs already. So this is the nose, eyeballs, the person is looking up. Then you can keep going. I guess this is the 0 position, 0.99 negative. So then you keep going down, no? So down to your nose, to your cheek, to your jaw, and then that's it. Yeah. So this is the brain. Do you notice something strange, Miss Lee?
Wait, go up a bit. Is there some... You can see left and right is not symmetrical, right? So you can probably tell, since you mentioned just now it's a cancer patient, there is probably growth. So the brightness of the tissue shows you that you have different or anomalous water content. Something is up there. You can compare the left side, which is healthy brain tissue, and on the right side, on the lower quadrant, that looks not very right.
Something's not quite right.
Yeah, something is not quite right. So while we can adjust the non-uniform field so that we choose to slice this way, and then it creates the kind of contrast image that we want. But at the same time, we can compare for symmetry, because human body is supposed to be very symmetrical. Not perfectly symmetrical, but very symmetrical. So if you see left and right not the same, there is a cause for concern.
So this is how it looks like slicing through the brain. So here are more brain pictures. Miss Lee, what are these?
You can see this is a picture of 2 twins, one with schizophrenia, and one is a healthy brain. So what you can see, that slightly butterfly shape, right, is actually your brainstem. All right, and you notice that the gap of the schizophrenic twin is actually quite big, meaning there's something wrong with that brain, lah. All right, so we can actually detect quite a lot of mental illness in brains, but MRI scans generally are not good enough, because MRI, you're just taking a picture. Anyway, talking about slices, this is a vertical slice. So previously we were talking, the one on top is a horizontal slice. We slice your brain horizontally. I mean, not slice. The imaging software slices the brain horizontally. Thanks. That's a very cute slicing technique. Oh, and this one slices vertically. Yep. So you can see this is probably the back of the neck. And then you can also see that there are hollow points. There's something wrong with the brain structure of someone with schizophrenia. But a lot of mental illness happens when the person is actually using the brain. So we would also like to take images of the MR of the patient when we give them certain stimulus, like we let them listen to some music, or we have a conversation with them, and we see which part of the brain have more blood flow, because blood is mainly water content. So you can see this person is supposed to be in a relaxed state, like you just sit in the chair and chill. So someone without PTSD, without trauma, or didn't go through significant events that cause them to feel that they're not safe, their brain is fairly relaxed, very green, very little blood flow. Whereas if you look at the PTSD brain, you tell them, it's safe in this room, you just sit in the chair and study some physics. The person's brain is like, not safe. And this one, sometimes you cannot tell until you put the patient into a scan. All right, so all this more colorful imaging, we will need fMRI, which is not covered in the syllabus, and the PET scan, which is coming soon in the A-level syllabus. Of course, if you're interested, plenty of stuff in the internet that you can find. So you can see this brain is another example of depression. So a normal brain, when given exciting images or videos to watch, their brain gets stimulated and they're like, oh, what is this? Oh, what is that? So interesting, so fun. Whereas the depressed person is like, I don't really care. I can't afford to pay attention. And you look at all the dark spots. The black spots are showing very low to no activity in pleasure centers, things that make you happy, things that make you excited, things that make someone want to reach out and connect. So mental illness, the fact that we can find out scans, and it's way more complicated than that, just showing some pictures. Is there another one there?
One more, yes. Wow,
Yes.
look
So
at this.
this is a PET scan. And you can see again the PTSD one just have more brain activity. The brain is just on overdrive. It's like the brain has a malware installed to
The brain
sucking up all
cannot
the...
chill. It's just like, calm down. The brain's like...
And the person or the patient might not even be aware that this is happening. So we hope that more brain scans in the future will help us understand a bit more about how humans are suffering and kind of help them as well. So be nice to people. You don't know what their brain is going through. Be nice to yourself. You also don't know what your brain is going through.
Until you get scared. Help. Yeah. So pretty interesting. Brain studies. If you're more interested, go study neurology in the future, or just go study psychology. One of those, you will see a lot of this thing lah. Okay, either one also can. All right. Back
Time to
to...
do past.
So past years, there are not very many of them, but when they do appear, you have to explain. That's the only thing. There's no calculation. What equation? Don't have. You have to explain all this. So let's look at how you can answer some of these past years and write beautiful mini essays. Okay, so let's start writing for this question.
So this question is, they came out twice, winter and summer 19. I'm guessing they wanted to test it twice. So here, let's read the question. Nuclear magnetic resonance imaging, NMRI or MRI, is used to obtain diagnostic information about internal body structures. State, during the use of the MRI, the function of the large constant magnetic field and the non-uniform magnetic field, or your secondary field. So I think the immediate idea that you should think about is, oh, we turn on the large field so that all the nuclei will precess, the P word, precess, along the magnetic field. So that would be the first point. You could say that it causes the nuclei to precess about or parallel to the direction of this large constant magnetic field. Okay, you can also add a point. You can say where the frequency of this precession is in, if you don't know how to spell, our friend Lamont is okay, just in the radio frequency range. All right, so where are the marks? If you say nuclei precess, like you at least remember that we are talking about nuclei and it's precessing, then this one will be 1 mark. Okay, and then about the direction of the large magnetic field, this is 1 mark. And the final mark is you talk about frequency. Frequency is in the radio frequency range. Okay, so the large magnetic field is just everybody come align and precess about the direction of the magnetic field. They are all spinning at their own frequency, which is in the radio frequency range. The non-uniform field is the field that causes able you to locate the nuclei. Okay, so you could say that this is used to locate or find the position of the precessing or spinning nuclei. Okay, this one is used to change. You want to scan your different parts of your brain or different parts of the organ that you're looking at, change the region where the nuclei are being detected. Okay, and it alters the frequency of precession because it is also another secondary magnetic field. So it causes that gradient or the different types of picture. Just like shining a light in your face will change the light intensity, this will alter the frequency of precession of the main magnetic field. So yeah, something like this, about 5 marks. Any 2 of these points is okay.
Nice. Next.
All right. Next question. Oh, so many lines.
Wow,
Stress.
this one write essay. This is from physics, not bio. Okay, lor. How many marks is this question, Miss?
8. It's a
Let's
do or
go.
die. It's
Let's
a do or
go.
die question. Okay, so main principles behind the use of MRI to obtain diagnostic information. So the previous question was just asking you what's the role of the uniform and non-uniform field. This one is tell the whole story. So you go once upon a time, or basically I will start the story with something that makes sense. So I would say that I will start with the patient. And patient is placed between the poles. Okay, the first field is the strong.
The main one.
What is the important word? Uniform. Magnetic field. What happens to the nuclei in the patient? The hydrogen.
Precess,
Nuclei.
align. That's your keyword right there.
Yes, need to make sure you hit the keyword. Precess. Or you could say rotate about the direction of this field. So this one is legit just writing again what we have written a few minutes ago.
But in
So
a more
now
compact
everything-
form lah.
Yep, you're right. Now everything is ready. We are ready to send in the pulse. You can write about the non-uniform field here also if you want, I guess. So we're gonna also talk about the non-uniform field.
Yeah, throw everything in lah. Because we don't know where the egg mask come from, so you just write everything.
True. So a non-uniform magnetic field allows different position of the nuclei to be detected. Okay? And remember the slicing? Different slices to be studied. So you got to plan your scan. You want to scan where? You want to slice how? How you want to apply the gradient field. All these are important. Okay, now we are ready to send in the radio wave. So after this, you can say the radio frequency pulse. The word pulse is important. Is applied.
So it comes in bursts. Pew! And then again, pew, pew, pew.
Then at the same frequency of precession, also known as your
Resonance?
Larmor frequency. Okay, so you're right, causing the hydrogen nuclei to resonate.
That's why they can get excited.
Resonate and get excited.
Higher energy state.
Absorbs
Go to a higher
energy.
energy.
Into higher energy state. Don't worry so much if you feel that your sentences are a bit weird. It's science, not literature. Okay.
As long as you
So
hit the points, you're fine.
Yes, and then you are describing the thing. So hydrogen nuclei now absorb energy, higher energy state, happy already. They are going to
Relax.
calm down.
Calm down. Why are you so excited? Calm down. Calm down, teacher.
So you can say when the hydrogen nuclei relaxes or undergo relaxation. Let's not be too casual here. It emits back the radio frequency pulse. Okay, So this radio frequency pulse is then detected
By
This
detector.
radio frequency pulse detected already. Then what happened?
Computer analyze though. I mean, they all have different parts of the body, got different relaxation time, different molecules. So you have a whole bunch of different radio pulses all coming out. So
So we
computer will
can write
process
all this code into the computer. But you have to write the keyword detected and processor. Okay, and the computer will do the imaging for you. So
Convert to
this
a
is
picture.
yes. So this is where we can stop already.
Nice.
8
Miss,
marks.
where the marks come from? Can we see the mark scheme?
Every
a bit?
color is 1 mark.
Wow, very nice. Can you scroll down to the mark scheme? I want to see.
Yeah, okay. Lie.
Okay. Oh.
So have to memorize all, my dear children, friends and family.
This is the only part where it's kind of like bio, where you have to just memorize and write.
So there are a different way of scoring. These are all B marks, meaning if you didn't write about the strong uniform magnetic field, you will lose 1 mark. If you didn't say that there's a radio frequency pulse, you lose 1 mark. So whenever you open a mark scheme of this kind of essay, especially for physics, they never bother to tell you the whole story, like what we did just now. They will just tell the examiner what are the key points that should be covered. So if you see something like this, be encouraged to write your own story. Because I think of a story, so I start. Patient is placed between poles of strong uniform magnetic field. There, strong uniform magnetic field, 1 mark, etc., etc. The bracket marks is any 2 out of 4, you will get full mark already. If you want to be extra and write everything, you can get 10 out of 8 marks, which will be then 8 out of 8 marks.
Okay.
Am I missing anything else?
Nope, sounds good. So don't memorize the whole paragraph. You know the points, or make the story make sense in your brain, then you can write a coherent piece. Yep.
Write your own story. You can take this as a practice. Like after watching this video, you can just take a while and then try to see how much you can recall and stitch together the story and then mark your own essay.
Yep, so I think that's all we have for the MRI. How it works, make sure you go and, make it stick in your brain how the MRI works, and you'll be good for this part. It's only appears once in a while, but when it does, remember must get ready to tell your story of the MRI.
Make your story your own.
So I think that's all for this video. I'll see you in the next chapter, because this is the end of magnetic fields. Congratulations, you're done with magnetic fields. But we will see more magnetic fields in chapter 23, the next one. So that's all for this one. See you in the next video.
Bye.